In this problem, we want to rank these molecules of, say, decreasing reactivity. So we're going to from the most to the least reactive. Most to least reactive. And here we need to consider the electrophilicity of the carbonyl carbon, and we also need to be considering the nature of the leaving group. So analyzing this molecule, let's say, leaving group here, when I do my nucleophilic acid substitution, the leaving group here will be chloride. So leaving group here is chloride. And then let me rewrite it. Leaving group, which is chloride here underneath, which we know that's a weak base coming from a very strong acid. HCl, the pKa here is -7. Very strong acid, weak base, and that makes an excellent leaving group. So here, my leaving group will be OR. So essentially, that's not a leaving group. If you think of that, not as an alcohol, but if it was leaving like an alkoxide, that's very bad leaving group, because this is a conjugate base of an alcohol, and the alcohols have pKa's around 16, much weaker acid, therefore stronger bases. So not a good leaving group. Here, when we do the nucleophilic addition, and again, all of these reactions here, let's say that I'm going to remove the symbols. We know the dipole is that way. Thinking of the mechanism that we did for acid chlorides and anhydrides, that will go nucleophilic attack to form a tetrahedral intermediate. So here I have a nucleophile. When you do that reaction, yes, you will form an under basic condition mechanism. Let's say that this is a chlorine, R, and that's my nucleophile. And then you reform the carbonyl. So essentially, to be reactive, you want this carbon as the more electrophilic it will be more reactive. One thing, so more electron deficient, so it will be better attack, say, or faster reaction when you have the attack by a nucleophile. And then you want a good leaving group. You're going through this tetrahedral intermediate. When you do the same for the acid, for the anhydrides, then the leaving group is not a chloride, it's not a alkoxide, it will be a carboxylate. And a carboxylate, you know, that is resonance stabilized, that's another leaving group, it's another good leaving group. The carboxylate is not as good as the chloride because, say that these are, the carboxylates are the conjugate bases of carboxylic acids. Say acetic acid, for example, pKa, if it is acidic, so this being a CH3, the pKa will be 4.7. So obviously much weaker acid than hydrochloric acid. So that's a stronger base, but still is resonance stabilized. So that makes a good leaving group. So already right here, I'll say that I'm ranking this most reactive than this, because again, we're analyzing in regards to electrophilicity of that carbon, chlorine electron withdrawing effect, and by induction, not as much by resonance, because chlorine belongs to another period below where the carbon is, so resonance effects are not important here. And it would be, in this case, so it's not the same as, say, electrophilic, that carbon. So it's still oxygen is more electronegative than carbon, but resonance effect kind of counteract that. In great leaving group, good, but not as great. So I'm going to be ranking this as number 1, and I'm going to be ranking this as number 2. And now I have this, I have included here an acyl phosphate, monophosphate. Phosphate, that's supposed to be an H. So in other parts, that will be O negative here, Again, we're thinking in that mechanism. Remember, instead of here is chloride of porting, but now we're looking at other leaving groups. The leaving group here, when that happened with acid phosphate, will have a negative here and say OR, O negative as well here. And this is similar to hydrogen phosphate, which is still, so this is 2 negative. Remember that phosphoric acid is a triprotic acid, and it will have the first ionization is lowest pKa, but here you will have conjugate base is dihydrogen phosphate, and this being the acid now, the other pair conjugate will be hydrogen phosphate in the conjugate basis, dihydrogen phosphate here, and now conjugate is hydrogen phosphate, 2 negative. It's not as a strong acid. There's one, so this will be a good leaving group, but not as great as that. So I'm going to rank this third. So next, I still have this too, the ester, and this is a thioester. We know this is a leaving group if we're doing that under basic conditions. So what is a leaving group if I am doing that with a thioester? Well, now the leaving group will be SR, so the conjugate base of a thiol. And thiols are more acidic than alcohols. I can't remember the pKa right now, but if you think that in the conjugate base, here the charge is in a much larger atom, so it's more dispersed. So this atom, this anion would be more stable than that. So it's better leaving group when you have a sulfur than when you have an oxygen. So reactivity-wise, then this will be number 4, and this is your last, number 5. And again, analyzing electrophilicity of the carbonyl carbon and the nature of the leaving group, we will see that the better the leaving group, the more reactive it will be.